Have you ever considered if we can upcycle plastic waste to value-added products, especially in an environmentally benign process? I'm Jerry Cao from the Department of Life Sciences at Chalmers University of Technology. Polyethylene terephthalate, or in short PET, is one of the most produced plastics and has been intensively used in our daily life, for example in single-use bottles, textiles, packaging, etc. However, it may take up to 48 years to degrade PET under ambient conditions. This could bring a huge challenge to our environment. Therefore, upcycle PET to value-added products, for example metal organic frameworks, is of interest. Since one of the main monomers of PET, terephthalic acid (TPA), is a common linker for MOF synthesis. MOFs are emerging porous materials with crystalline structures and widely used in gas absorption, catalysts, sensor, drug delivery, etc. Current PET-to-MOF upcycling often involves hazardous catalysts and harsh process conditions. In our recent letter to ACS Sustainable Chemistry and Engineering, we reported PET-to-MOF upcycling using enzymatic degradation, where the PET can be depolymerized under mesophilic conditions. Now, my colleague Xiaozhi will tell you more about how PETase works.
Hi, I'm Xiaozhi. I also work in Chalmers University of Technology, and I work on protein engineering. Here in this project, we utilize a PET degradation enzyme to degrade PET, which is called thermopetase. This is a thermophilic version from its original ispetase, which was isolated from a bacteria from marine environments. The thermopetase could degrade PET into its monomers, TPA, MHET, and a little bit BHET, and also ethylene glycol. And all those monomers could be measured by HPLC. We express this thermopetase in E. coli, and we could also purify the enzyme from it. The enzymes could be purified. However, in the purification process, we need to play around a large amount of washing and elution buffer. This process is definitely not that sustainable. Then we also came up with the idea of using the crude cell lysate to degrade PET. This PET material used in our paper is actually found in the restaurant from Chalmers campus, which is a yogurt container. The TPA could be both recovered from the two systems. However, the crude cell lysate contains not only the enzyme, but also some other impurities, like DNA, glucose, and metal ions. And those might also be precipitated together with TPA in the TPA recovery process, and might also affect the MOF synthesis process.
After enzymatic degradation, we observed lots of holes on the surface of PET, which confirms the PET degradation. As mentioned by Xiaozhi, the concentration of the produced TPA after 48 hours can be determined by HPLC. After the TPA collection, we verify the impurity levels of the obtained TPA. Both NMR and the TGA results indicate low impurity levels in the enzymatic recycled TPA. Thereafter, we use these obtained TPA as the organic linkers for MOF synthesis. According to the XRD patterns, we confirmed the crystallization of the MOFs. By comparing the geometry of the MOF particles, we observed that using TPA from lysate could lead to a lower crystallinity and suboptimal synthesis conditions compared to using the purified PETase. We also tested the thermal stability and BET surface area of the obtained MOFs, and the MOFs with recycled TPA as linkers showed comparable performance with the MOFs synthesized using commercial TPA. And we verified the feasibility of MOF synthesis using Enzymatic recycled TPA with 3 different MOFs, including MOF5, MIL101, and UIO66. We believe our findings can stimulate more interdisciplinary studies between reticular chemistry
and bioengineering,
and contribute to a more sustainable future.